So we ask AI to do pretty much everything for us, right? Write our emails, our code, even our poetry. But have you ever really stopped and wondered what's actually going on under the hood? I'm not talking about the science fiction stuff. I mean the raw nitty-gritty mechanics. Well, today, we're going to pop the hood on the engine that powers almost all of modern AI, the transformer. And that's the big question, isn't it? We see these polished outputs, these responses that feel, well, almost magical sometimes. But how does a machine really go from a string of our words to generating a totally new, coherent idea? That's the black box we are prying open today. All right, so here's the first and maybe the biggest hurdle. Our language is messy. It's filled with nuance and context. Computers, well, they only speak one language, and that language is math. So the very first job is translation, turning our world of words into their world of numbers. Now, this whole translation thing kicks off with a process called tokenization. Instead of trying to memorize every single word that exists, which would be impossible, the model breaks them down into smaller, common chunks. So a word like unbelievable becomes three separate tokens: un, believe, and able. This is just super efficient. It keeps the vocabulary manageable, and what's really cool is it lets the model understand new words it's never seen before just by recognizing the parts. Each of these little tokens then gets its own unique ID number. But, those numbers are just labels. They don't mean anything yet. This next step, this is where the real magic happens. It's called embeddings. Think of it like this. Each token is given a set of coordinates, placing it on a giant, complex, multi-dimensional map. And on this map, distance equals meaning. So words like king and queen are going to be really close together, but king and, say, car are going to be way far apart. This is how the machine starts to actually grasp the relationships between concepts. And this is the truly mind-blowing result of that process. Because words are now just points on a map, you can literally do math with them. The relationship, the vector from man to king, is almost identical to the vector from woman to queen. So you can take the king vector, subtract the man vector, add the woman vector, and you land right next to queen. Think about that for a second. These really abstract human ideas like gender and royalty have become simple arithmetic. This is the moment language truly becomes computable. Okay, so we've turned words into math. Awesome. But language isn't just a bag of words, right? Context is everything. For years, this was a huge problem for AI models. They just read word by word. And then a breakthrough happened that changed everything: the transformer architecture. See, before the transformer, old models had to process text sequentially, one word at a time. It was like trying to understand a whole movie by looking at it through a tiny keyhole. By the time they got to the end of a long sentence, they'd totally forgotten what happened at the beginning. The transformer just blows that keyhole wide open. With a mechanism called self-attention, it looks at every single word in the sentence at the exact same time. Let's look at a classic example to see what I mean. The animal didn't cross the street because it was tired. Now, for you and me, it's obvious, right? We know what it refers to. But for a machine, this is a real puzzle. Does it mean the animal, or does it mean the street? A street can't be tired, but a computer doesn't know that instinctively. And this is precisely the problem that self-attention was built to solve. For that little word it, the model calculates a connection score to every other word in the sentence. It quickly figures out that the links to animal and tired are super strong, while the link to street is really weak. By weighing all of these relationships at once, it just instantly solves the puzzle. But wait, there's a catch. If you process everything all at once in parallel, you kind of break something else in the process. You lose all sense of word order. To a pure attention mechanism, the sentence dog bites man is exactly the same as man bites dog because, hey, they've got the exact same words. And yeah, that's a huge problem. So, how did the engineers fix this? With a really clever hack called positional encodings. It's basically an extra bit of math, a unique signature that gets added to each word's embedding. This signature doesn't describe the word's meaning, it only describes its exact position: first, second, third, and so on. It's a simple little patch that lets the model have the best of both worlds: the full context from attention and the crucial order of the words. Okay, so those are the big pieces. We have tokens, embeddings, attention, and positional encodings. Now let's put it all together and see how they actually generate text. How does a machine go from just understanding our language to creating its own? For all the complexity we just talked about, the way it actually generates text is a surprisingly simple loop. It takes your input, it looks at every single word it knows, its entire vocabulary, and computes the probability for which word should come next. Then, it samples one, it picks a winner. That new word gets tacked onto the end of the input, and the whole process just repeats, one single word at a time. This is why it's called autoregressive. It's constantly feeding its own output right back into itself to figure out what to say next. And that simple loop, that's what's running every single time you chat with an LLM. But why does any of this matter? Why go through all this? Because knowing these mechanics isn't just trivia, it's absolutely crucial if you're trying to build reliable, cost-effective tools with this tech. This is where the theory hits the real world. First thing you have to get straight is the difference between training and inference. Training is this colossal, multi-million-dollar process. It's like forging the entire engine from scratch, where the model learns by adjusting billions of tiny knobs. But inference, that's what you do every day. That's just turning the key and driving. The engine is already built, its parameters are frozen. This is the key insight. It's why you pay for the number of tokens you use, not for how long the computer sits there thinking. Next up is the context window. This is the absolute maximum number of tokens a model can look at any one time. It's basically the model's entire short-term memory, and while these windows are getting bigger and bigger, they're still finite. It's also worth knowing that research shows models are way better at remembering stuff at the very beginning and very end of a long prompt. There's this weird effect where things can get lost in the middle. So, what does this all mean for you? What are the big takeaways? First, remember these things are probability machines. They are making statistical guesses, not looking up facts in a database. Second, tokens cost money, every single one. Shorter, more precise inputs are always your friend. Third, that context window, it's precious real estate. It's the model's entire world, so you have to manage it carefully. And finally, really understanding these fundamental mechanics is what separates a casual user from a true AI engineer who can build something powerful and predictable. Look, when you really get the guts of this machine, from the tokens all the way up to the attention mechanism, you're no longer just a passenger along for the ride. You're in the driver's seat. You understand its power, but you also get its limits and its quirks. The black box is officially open. So the only question left is the fun one. Now that you know how it thinks, what are you going to build with it?